Hello everyone, I'm Venkatesh from the Applied Data Science Lab at IIIT Delhi. Today I'm going to present our work on towards paraphrasing algebraic word problems. This work was carried out in collaboration with Rishabh Gupta, Mukesh Mohania and Vikram Goel. In today's pedagogical scenario, we observe that online learning platforms have proliferated all education spheres, especially the K-12 education system. We observe that most of the evaluations are carried out online, especially in the pandemic situation. We, in particular, would like to focus on the subject of mathematics, where students are observed to usually memorize solutions to problems or plagiarize from others' solutions in case of unproctored exams. This is common in the K-12 system where students actually memorize the approach or solutions and are able to apply those patterns to the same problems. Hence, there is a need to generate diverse problems. This becomes very cumbersome for academics to come up with new problems for the same concept as it is a manual process. Hence, we propose a novel problem of paraphrasing math word problems where we preserve the numeric entities and also the grammar such that the solution to the original problem is the same, but the question is paraphrased in such a way that students have to actually read the problem to understand the concept behind it and apply the methodology. But even before paraphrasing, we observe that existing language models do not generate good paraphrases, and there are no existing measures to measure the quality of paraphrases, keeping the numerical quantities in mind, which is a characteristic of the algebraic word problems. Hence, we propose a novel method to score the paraphrases, which we term as ParaQD. And our method is completely self-supervised in the sense it doesn't need a manually annotated paraphrases for each math word problem. Here in this figure, we observe that the given math word problem is Anna ate 6 cookies, Samantha ate 4 more cookies than Anna. How many cookies did Samantha eat? We observe that existing language models lose most of the information and only give the last part of the sentence or the first part of the sentence. Most of the existing language models do not preserve the numerical quantities nor the concept in the original math word problem. But we observe that existing paraphrase scorers, which are indicated by X here, output a very high similarity or score, indicating that these are actually good paraphrases of the original math word problem, when that is not the case, as these problems are no longer solvable. But we observe that in the branch labeled by Y, which is our proposed novel method, the score is negative, indicating that it's a bad paraphrase and should not be accepted. Now, coming to the approach of our problem, the main goal is to paraphrase method problems to generate multiple variants of the original problem, but we want to preserve the grammar and also the numerical quantities. Hence, we propose to train a scoring model that can detect the changes in numerical quantities and also grammar simultaneously. This problem has not been tackled before, as existing semantic similarity models only aim to preserve the grammar. And also existing augmentation methods, existing paraphrasing models do not rely on self-supervised methods or augmentation methods. For each input sample, that is the math word problem, we have several novel augmentation operators that generate positive samples, which indicate good paraphrases, and negative samples, which indicate bad paraphrases, which are then passed to an encoder to generate vectors, which are then compared through a triplet loss. The triplet loss acts like a tug of war mechanism where it tries to bring the anchor sample, which is the original math word problem, and positive samples closer and pulls apart the negative samples. The positive and negative samples are generated in a self-supervised way using several augmentation operators defined by us. Some of the positive augmentation operators which generate positive paraphrases are back translation, which basically translates the original math word problem to German or Dutch and then translates it back to English, where the words are replaced, hence generating some diversity. We also have identity transformation where the original sample is given as such. This is done just to make sure that the model does not, that the negative augmentations does not collapse the vector space. And we also do a number to words transformation where the numbers in the original input are actually transformed to words. For example, If Ram ate 2 apples, where 2 is given as a number, it's replaced by TWO, as both of these are equivalent and it's a positive paraphrase. We also do unit expansion where M or MM are converted to meters and millimeters. Some of the negative operators are most important phrase deletion, where we use a ranking algorithm to detect the most important phrases in the math word problem and delete them. This is because when most important phrases such as Ram had 10 apples and he had bought 2 more oranges, how many fruits did he have? Here, if apples or oranges or fruits are deleted, then the problem does not make sense anymore and it renders it unsolvable. And we also delete the last sentence, which is usually the question, which usually frames the question which the student has to solve. We do this because we observe most of the language models have the phenomenon of hallucination or forgetting where they do not generate the last sentence. We also do named entity replacement for the same reason that we observe that some named entities were replaced or lost. We also do numerical entity deletion as when numerical quantities are missing, the problems become unsolvable and hence it's a negative paraphrase, though it is grammatically correct. We also use the Pegasus language model as one of the augmentation operators, as we observed that for math word problems, most of the paraphrases generated by Pegasus were wrong. We also do this because Pegasus is one of the recent state-of-the-art models for paraphrasing generic English text. We also do unit replacement where units like meters or kilometers are replaced with the closest units or they are deleted. This is again done to ensure that when paraphrases have missing units, they are assigned a low score because it makes them unsolvable. We can observe the embedding plots here, where we observe that the anchor and the positive are close together as indicated, and the negatives are clustered far apart together, indicating that our proposed method is able to separate bad paraphrases from good paraphrases really well. We compare our method with several baselines, which involve self-supervised or unsupervised augmentation methods like unsupervised data augmentation and self-supervised augmentation method SSMBA, which is again a text augmentation method. We also use a default pre-trained by-encoder model to indicate that our proposed learning method is superior to the default scoring models, which are already available. Here we observe the results of our table where we report the macro precision recall and F1 scores and weighted precision recall and F1 scores. We also report a new metric mean separation where we indicate how the positives and negative similarity metrics are well separated. This is just to indicate that positive paraphrases have a very high score and the negative paraphrases should have a very low score. We observe that our model is able to achieve this where the mean separation between positive and negative scores is 0.78, whereas it's very low for other models, indicating that mostly positive and negative paraphrases on an average have similar scores. We also observe that we have the highest F1 scores, outperforming all the remaining models by a huge margin. This result is reported on the acquired dataset open source by DeepMind, which consists of algebraic and math word problems. In future, we plan to use the scoring model as an objective in a reinforcement learning framework to steer the language models to generate better paraphrases. Thank you.